Hello all, welcome to my channel. I'm back with another video. In this video, we will continue the feature platform series that we are doing. Uh, in my previous blog, I had discussed all the structures that were or all the tools that many companies use in their feature platforms. Like we have seen how companies are using Redis and what you call SDFS or other tools for their feature platform. What I thought in this platform, this blog we will be creating, I will try to present an idea of how we can create a feature platform on a Lakehouse system. So what has happened in recent times is Lakehouse or what you call warehouse plus lake solution combination is coming up and coming architecture that is being used at many companies because of their scale and so in this case, what we will be trying to build is a feature platform which is completely running on the Lakehouse solution. So we are not using any specified warehouse compute and everything. We will be using disaggregated storage and engine. So let's see what is the structure of this platform will look like in case we build it on a Lakehouse solution. So there are three components we have seen majorly which are there that we have to do when we are building a feature platform is one is the feature source ingestion, then we have a feature computation engine, and then we have a feature serving engine. So and the part that we want to improve upon is because if we build the system on Lakehouse, we don't have to worry about the storage capacity and all because we will kind of get an infinite scale, and then we will have to do some what you call maintenance to make the cost reduce by purging old data if it is not relevant, so that will still be there. So what we are proposing or we are thinking in this regards is that the real-time engine of Flink, sorry, not Flink, of the feature platform can be served from a Lakehouse solution called Paimon, and the offline mode can be served using engine. I mean, not engine. It's a storage format called Iceberg. And the computations in the real-time form will happen using Flink, which what it will do is this Flink, what it will do is will read from Kafka or Fluss. Fluss is another very good system which is coming up and coming and which can replace Kafka in future as well for analytical purposes. So Kafka or Fluss, wherever we receive the model inputs, which is not transformed yet. So that will be created, the features will be created out of it using Flink and then persisted into an open lakehouse solution format called Paimon. And then it will be served for real-time consumption as well because Paimon supports real-time ingestion as well as real-time serving on Lakehouse using object storage. So this is where this online serving comes, and then we will have another engine, another job which continuously offloads the Paimon's real-time data to an offline system, which will be hosted on Iceberg. What it does, it will compute the aggregated values. Let's say we have not aggregated, I will say it will just simply offload the data from Paimon to Iceberg so that it can be consumed in the model training and offline feature serving. And that we will again we will not persist the data. It will be used by, for example, Doris or Star Rocks. These are MPP systems which does support external Iceberg location as the database source. So what will happen that we will not with these will only do the computation which is on the data which is residing on S3 in Iceberg format. Online serving will happen from the data which is on S3 based on open table format called Paimon. Flink will do the computation for real time, and for offline computations or transformation we will use Spark to do the compaction, aggregations and other things, and then we will have one unified catalog which can work with both Paimon and Iceberg. And then the online serving will use the Paimon catalog to get the features, and the offline mode will talk to the Iceberg catalog and then get the features and then do the training. So this is the overall architecture. The feature set of this is streaming. I mean, because we are relying on Flink to do the real-time processing, so this engine becomes stream native. There is one unified compute path, like both all the aggregations are being done, all the feature transformation is being done by Flink itself. And then the data is fresh. Fast features are online because this Paimon is serving the data, which is almost near real time. And then same data is being copied to the offline system. So hence there is no what you call gap between or there is no gap between the real time and offline systems. And there is no vendor lock-in because all these tools that we are using are open source. Components wise, feature registration system, that system to define the features and everything. Then we have a feature store which is based on this Iceberg and Paimon based open table formats. Feature serving is done from these three systems itself, which is low latency feature retrieval and ML will happen, and feature offline feature serving will happen using Doris or Star Rocks because we have to do some computation in there. Feature registration. So what it will do is it will store the metadata about the features, name, data type, freshness, owner tags, lineage, and stuff like that. It will track what the features are materialized from, like whether it is materialized from Paimon or Iceberg. Then can be built using DB plus REST API. And then it will integrate with Fist or other open source alternatives like Tecton, SDK, and Metadata DB. So this will become a centralized registry. Online feature store, as I mentioned, it is powered by Paimon, and the reason Paimon is being used is Paimon supports streaming rights and low latency rates, making it ideal for online feature serving, and it handles incremental updates as well. So if we have to update something, we can do it in real time without have to rewrite the files whole thing. So this also it has Flink change log support, so it can be, and it is very much integrated with Flink engine. So this is why we are using Paimon as an online feature store. Then we have Iceberg as an offline feature store because it supports ACID transaction, schema evaluation, partitions, and everything. So it makes suitable for large scale analysis. And then it also supports snapshot feature, so we can do model training. We can go back in time and see at a certain stage what were the features. It can do batch scoring and everything. It so that's why we are using Iceberg as an offline feature store. Then for online feature serving, how we are serving is we are using a catalog to talk to the Paimon tables and then query the features that we want. So if we have need of ultra low latency, we can have a here only we can have one more process that publishes the latest data to Redis systems as well. If we have means full real time requirement, then we can have an ultra low latency DB there as well. Otherwise, in general, if we don't have ultra low latency number, for example, less than 10 milliseconds, then we don't, means if we can sustain till 10 milliseconds, we can serve via Flink itself. But if we have microsecond latency requirements, then we'll have to use Redis because Paimon does not support microsecond level latency as of now. It will only support till milliseconds. Then we have fast offline serving using Doris, ClickHouse, or Presto. We can use any MPP database in here. It doesn't have to be these like Presto, ClickHouse, Doris, Star Rocks. All will behave same because they all have support for external Iceberg tables, and connectors will be provided for Iceberg and Paimon, and they can read it from there itself. So there are three different metallization paths. So Kafka, from Kafka to Flink to Paimon, which is the first path. Then that is called stream compute. This will be used for online feature store. Then we have Kafka, Flink, Iceberg. Then Flink CDC to Iceberg, which is again a stream compute, which will be for offline feature store. Then we have Iceberg to Spark to model training, which is batch for training scenarios. And then Iceberg to Doris, which is a fast OLAP for offline inferencing. So these are different materialization paths. Consistency, because online offline we are using Flink DAGs to materialize both Paimon and Iceberg, so there is only one compute engine running. So time travel for training is supported via Iceberg snapshots. Point in time correctness is supported by timestamp, event timestamp plus write timestamp, and we can use SCD as well. And backfilling will be done using Spark plus iBugs for batch recomputation and Flink for continuous updates. So this is how the consistency will be managed for this particular system. And other optional enhancement that we can do is we can make feature lineage URI to see how the feature is getting calculated from source to destination. Then feature testing framework to link on to find on the drift and other spikes that is happening, and dashboards for model observability and feature uses. So this, if we build a system around this, we will. I'm pretty confident that we can build a system or a feature store that is scalable and easy to maintain, and having full what you call control over our systems, and that way we can make a good feature store for ourselves. That was it for this video. We'll see you in another video. Till that time, have a nice day, and if you like this video, do support the channel. Thanks.